Hey everybody, today we are going to be covering thermal and vibration damage equivalence analysis. This is going to be the first out of two lectures for today, so I'll cover this one and then also have one in physics of failure, which has a lot of relatable topics. So let's go ahead and get started. Here's the agenda. Go through an introduction, talk about the learning outcomes, a couple of definitions, and then some of the requirements to test. And then specifically we'll get into the thermal failure mechanisms and acceleration methods, and then the vibration failure mechanisms and accelerated methods, and then summarize for this lecture. So to kind of start out, accelerated test methods provide a means of producing equivalent damage in a shorter period of time for a specific failure mechanism. So essentially what that means is, given that there is a failure mechanism that can occur within a system or a part, we can use accelerated test methods in order to find that failure mechanism faster and understand essentially how long it'll take to get there. And so a lot of what we're going to look at today is kind of the equations and the math behind understanding what it takes to get to that point. It's important to understand there is usually a specific physical phenomena that creates a failure mechanism, and it's specifically that one that's being accelerated. And the third bullet point here is kind of related, and that basically says that there's not one model that looks at all the failure mechanisms, all these causes of a failure, all at one time. And so we kind of have to look at them one at a time. So we look at each specific failure phenomena kind of one at a time. The two most common environments, as we've already discussed previously, are thermal, so temperature, either temperature swings or extremes, or the ramp rates or the shock of the thermal, of the temperature, and then also the vibration. Okay, so today's learning outcomes include discussing the reliability engineer's role within accelerated test methods, and then describing the thermal and vibration accelerated test methods with kind of the knowledge of the theory behind it. So explaining the aging model, the low cycle fatigue model, and explaining the frequency spectrum control accelerated vibration test damage equivalence. Okay, so this is an important slide here. There are essentially four primary thermal failure modes, which are shown here. So first is aging, which is a degradation of mechanical and performance properties due to high temperature exposure. So I've already mentioned this several times, right? This is the idea that something ages faster due to a higher, more extreme temperature. Fatigue is the second one, in this case low cycle fatigue. Low cycle fatigue is continuous cyclic expansion contraction from material coefficient of thermal expansion. So that's a CTE mismatch between two materials that we kind of talked about last week. And essentially what that does is when things expand and contract, they change at different rates, and that induces stress in the material, and over many cycles, then it essentially causes some sort of crack, which of course then grows over subsequent cycles, and then eventually essentially breaks apart. Some sort of actual yielding occurs at some point. The third kind of thermal failure mode is fracture, and this is at low temperatures. And so essentially materials lose their elastic properties and become brittle. And that's where there's an actual separation. Brittle as opposed to being ductile. So ductile materials have a little bit more give, a little bit more elasticity. Brittle materials have a lot less elasticity. So when they get deformed, or when they take on strain, so when they take on some sort of deformation, they tend to crack and break a lot faster. So what happens in the fracture is that at low temperatures, they become brittle and they break. Finally, creep. So this is, as opposed to low temperatures, this is more related to high temperatures, and specifically with loading being force, right? So at high temperatures with loading, and loading essentially induces stress into the material. So essentially at this high temperatures with loading, there's a deformity of the material, so it causes the material to change its shape, and that can cause essentially a rupture, and ultimately, it exceeds the yield strength, and it causes it to actually break. There are essentially three different thermal test acceleration methods that we'll discuss. The first is Arrhenius aging, which is the Arrhenius model, and it's kind of known as steady state temperature equivalence. We'll cover the low cycle fatigue, which is based on thermal cycling, things like the delta T, or change in temperature, rate compression, dwell times, things like that. And we've covered some of these ideas, some of these variables in some of the other lectures, but we'll look at them again today. And then finally, thermal shock. So the temperature rate of change, or the delta temperature damage equivalent. Okay, so first off, before I get too far into this slide, I'll point out that there is a previous slide I'm not going to talk to, but this discusses a little bit about how to get to the model that's on this slide, essentially. So it's a little bit of the derivation and some of the theory kind of behind the Arrhenius equation. But I'm not going to go over that in detail now. I don't think it's particularly relevant to today's lecture, so I'll skip over it. But what this essentially shows you, what the AF stands for, first of all, is acceleration factor. And very similarly, RF is a reduction factor. So it depends on kind of the angle at which you're looking at the problem. And essentially, what this is telling you, and we'll think about the AF, which seems to be kind of the more typical form of the equation, essentially is how much of an acceleration factor you can get out by increasing the temperature of a test. Meaning that, for example, if we're looking at a particular failure mode, and it's for a particular type of component, so we know some information about the component, we can say that the component normally has a life of 10 years and goes through kind of traditional diurnal cycles where most of the time it's between 50 degrees and 90 degrees, but a few days out of the year it's between, we'll say, 30 degrees and 110 degrees, and maybe even fewer days it's as cold as 5 degrees outside and as warm as 130. Maybe it's in some sort of chamber or bunker that's not being controlled. The environment's not being controlled, right? So we can think about a component that would live for so long, and at some point, maybe would have a failure as a result of one of these failure mechanisms. And the question might be, how can we accelerate in a testing environment the precipitation of that failure mechanism? So how can we find it faster? And if we do find it faster, so let's say maybe we don't know exactly when it occurs in reality and we're interested to understand that, we can set up a test at extreme temperatures to find the failure faster, and then essentially deduce out of that when it would occur given the life cycle of the system. What the component or the system would see in reality. Okay? So some of the variables you're seeing here, one, the K is the Boltzmann constant. E sub A is an activation energy. We'll talk about those, not K. K is a constant. We're going to kind of just leave that one be. The activation energy we'll talk about more shortly. T1 is the normal service time at temperature. At temperature T1. T2 is the compressed aging time at temperature T2. And then capital T1 is the normal service temperature, right? So this is kind of typical temperature of the item. And T2 is the accelerated aging temperature. So first, a little bit on activation energies. The values of these range anywhere from about 0.2 to 2.2, so they don't actually cover a huge range. Obviously, they'll change the result a fair amount, but they don't have a huge range of values. This second bullet point gives an idea of what sorts of materials have what sorts of values. So polymers, unfilled polymers have like a 1 to a 1.5. Unfilled nylon 66 has a value of 1. Glass-filled polymers like a 0.7 to 0.9. And you know, there's some other examples. The nylon 66 with 15% glass is a value of 0.09 or 0.9, and so on and so forth. The point being that the way that we choose the activation energies is by looking up the material and understand what the activation energy is for the particular material. So it's essentially, I mean, it's a material dependent sort of value, and that makes sense, right? Because if we're looking at something cracking, a failure mechanism that ultimately causes cracking as a result of temperature cycling, then it would make sense that different materials would handle that differently. And this activation energy factor or parameter is what governs that process. So, and you can see there are some other values in here as well. And then on the bottom right in the box, there are some good references that have these these activation energies in them. So you can look them up there. Okay, and as an example, we'll do more examples in a little bit of the Arrhenius equation, but just to give a real quick kind of high-level example, not to really show the math, but just to kind of give an idea of the value and kind of what's going on. We can look at this graph first and say that, first off, this is an example component that has a 10-year life cycle, and the graph is depicting essentially the amount of time that component spends at the given temperature. So as you notice, the x-axis is temperatures, meaning that we'll say, and then the vertical axis is time, right? So if we look at this bar here in the middle, that essentially the component spends roughly a little over 2,000 hours around this 85-degree temperature. So this gives you an idea. This is essentially the distribution of temperature it sees over its 10-year life. So we can apply the Arrhenius equation here, and it's actually a slight tweak on it where it's actually solving for T1 instead of an acceleration factor. But essentially, we can put the data in from the previous chart, which essentially is converted. It goes into these first two columns. And as well as the time, and we can put some factors in up here, right? So we know the acceleration or the activation energy, we know the constant here, and we're assuming some sort of test aging temperature. And by doing that, we have to do the Arrhenius calculation for each line in here, right? So this was set up in an Excel spreadsheet. But essentially the point of all this is that we can sum up this time and say that at 125 degrees Celsius, it'll take 1,821 hours in order to get to a particular failure mode. All right, so essentially it's saying the acceleration factor would be the 1821 divided by, well, actually I say that backwards. The acceleration factor would be the total number of hours, right, 10 years, divided by 1821. The reduction factor would be 1821 divided by the 10 years. Okay, so that gives you an idea. Now, if we instead were to redo this spreadsheet with a different value up here for temperature 1, instead of 125, we did 150, we would only have to test for 460 hours. Okay, right, so that shows an even higher value of an acceleration factor. And if we continue to move this up, we would expect the test time in hours to be going down. So there are a couple of common questions that come up when using these types of models. And so I wanted to address those in kind of a question answer format here. First of all, how does someone choose an activation energy to utilize? Well, I've shown you how to kind of pick it, right? There's some resources. We choose it based on the material. And depend. So if you have a part, the kicker might be that the part has multiple materials in it. So the question it becomes, which one's going to be limiting? And, of course, it would take a little bit of work, and you might have to be more of an expert in order to really quickly be able to do this. But essentially, if all the other test parameters are the same, the lowest activation energy will cause the first failure, essentially. So if you're going to be looking for a failure mechanism in a part, you'd want to go with the material with the lowest activation energy. And that really answers the second question as well. If there are multiple materials, you would choose the one with the lowest activation energy. But that would depend if it's multiple materials and it's in different parts. The only thing to be careful of there, because we typically assume that a part sees all the same temperatures. But if you have a part that's in one section of your system and a part in a different section of your system, and for whatever reason you're comparing those, it's important to understand that some of the other variables in the Arrhenius equation could change. One could see a different set of temperature swings than the other. And that means you have to actually assess them both. But again, in general, if it's part of one system, it's usually going to be the one with the lowest activation energy. So just kind of be aware of that. The final point here is specifically about the sensitivity of the the activation energy. And it turns out that it is actually pretty sensitive. Highly sensitive might be a stretch in terms of the semantics here, but changing the value of the activation energy can certainly change the results. It's good to know, though, that by changing the activation energy, you're essentially saying that you have a different material. So that's a pretty fundamental change. The point being that you want to be aware of choosing the right activation energy. And to be honest, in practice, it's not all that easy. And so, it's one of those times where you almost want to convince yourself force yourself to choose the lowest possible activation energy, and then force yourself to be convinced to choose a higher one. And I'm not usually a fan of choosing kind of the most extremes to make it look the worst, but in this case, because it's a sensitive variable, you could end up in a situation where your math was pretty far off if you chose kind of a middle of the range value and it ended up being a low value. So that's just something to be careful of. And you can, in your particular situation, if you're looking at a particular scenario, you can do a sensitivity analysis, right? So if you have an activation energy and you think that the value is between 1 and 1.4, you can look at what is the acceleration factor with a value of 1, what's the acceleration factor with a value of 1.4, and that gives you an idea of kind of how sensitive the acceleration factor is relative to the activation energy. And you can use those results accordingly. So aging is one thermal factor, but thermal cycling damage is a separate thing which we need to investigate differently, and that's where we are headed now. So thermal cycling is very, very intimately tied to this idea of the difference between two materials, CTE, or coefficient of thermal expansion, or we call the CTE mismatch. That's probably its most common term. And the next slide has a really nice picture of essentially what that means. So I'll show that in just a second. But as a quick description, a product that's made of two different materials, or whatever it may be, it could just be two different materials that are adjacently adhered, right? So it doesn't have to be within a particular product. But two materials that are attached in some way, and they have to be actually attached. They can't just be next to each other. And if they're allowed to slide relative to one another, it doesn't really matter. It's only materials that are genuinely attached. What happens is when they heat up and expand, they expand at different rates, and that causes one essentially to be bigger than the other, which stretches the one that stays smaller gets stretched out. The one that wants to expand bigger is essentially compressed down, and it causes a lot of stress right at the intersection. And that's that being done over and over and over, hence the cycle, causes an accumulation of damage. And once then there's enough accumulation of damage, then there's essentially a failure, right? So little cracks form, the cracks grow, and essentially they separate. So this is typically modeled with the low cycle fatigue damage model, very commonly referred to as a Coffin-Manson model. So something that's very easy to look up online. Also, as temperature change rate, creep effect, and high aging temperatures become bigger factors, you can expand to the more kind of full-fledged Norris Landsberg model as well. So that's kind of a heavier version of the Coffin-Manson model. Okay, so to give just a little bit more on this idea of CTE mismatch, we'll say in this example here where we've got kind of a blue, green, and orange box, that each one of these represents a material, and material 1 has the greatest CTE, coefficient of thermal expansion, so it's going to expand the most given a change in temperature, right? So each of these materials will see the same temperature, right? Same temperature change, so they may go from 50 to 90 degrees, okay? So the CTE1 for material 1 is the largest, and so it's going to expand the most. CTE2 is a little bit smaller, so it'll expand the second most, and the CTE for 3 is the smallest, so it'll expand the least. And what happens is in the picture on the left here, where everything's a perfect rectangle, this would be before any temperature change exists, okay? What happens on this right side is this is once the temperature has changed, the materials have expanded, we can see that we no longer have rectangles, right? We have essentially trapezoids. And what this represents is on the top side, we have what's likely a full expansion of the material. On the bottom side, you notice that what should be the same length as the top side is shorter, and the reason it's shorter is because it's being pulled in by material 2. The material 2 is constraining this. What's interesting is that this little portion, this lip on either side, is actually expanded at its full rate because it has no reason why it can't expand. And the same with the vertical side. So it's allowed to expand essentially as much as it wants. But it's this region where there's actually an attachment where 1 is being constrained. Okay? Similarly, 2 has expanded beyond what it would like to expand because it's being pulled by 1 to expand more. So you have these 2 that are in opposition. And the same thing happens between 2 and 3. So the result is that there's a significant amount of stress, and the stress is particularly at these interfaces. And it's of course in other areas as well, but the stress concentrations are at these interfaces, and that's where you see the failures as a result of the CTE mismatch. Building off something we've previously talked about, a product's response to a change in temperature is important to the damage in which it occurs. So essentially this equation in the middle of the screen is showing the rate of change of temperature. So as something increases or decreases in temperature, it has an ability to take on that temperature, either slowly or quickly. So we see this, there's first of all the T ambient, so the ambient temperature, and then the product's temperature itself. And as something's being heated up, or let's say it's already warm or cold, and it's trending toward an ambient temperature, for example, it has an ability to take on that temperature, which is essentially dictated by M sub T. which is known as the thermal mass. And this value is not actually a mass. It's an ability for essentially a specific heat. It's an ability to take on heat. And so the greater the thermal mass, the slower the temperature transition. So it has an analogous to physical items and things like position, speed, acceleration, and so on and so forth. And it's important to note that, kind of like in a theoretical sense, there's no pure thermal shock, meaning that you can't, in all cases where you heat up the air around a product, the product's actual temperature will lag that thermal temperature on the outside. So if we start at ambient and we heat up a chamber, and we heat up the chamber, let's say from 70 degrees to 100 degrees, once the chamber hits 100 degrees, the product's temperature will never be 100 degrees at that point in time. There's always going to be some period of time where the product has to catch up to that ambient temperature. And that's essentially what we would refer to as dwell time. So we have to sit there for a while and wait for the product to catch up. That's shown nicely in this image here, where it's labeled well too, right? So the blue line is the temperature of the chamber. So it starts at 20 degrees Celsius and it's going up to 120 degrees Celsius. And of course it gets there pretty quick because we can heat air quite fast. But essentially the thermal mass of air is very, very small, right? The thermal mass of a product, of a more physical item, is much, much higher. And so that's why we see this red line lagging, right? And the idea when we run these thermal tests, because the way that our models work, we assume temperature values, temperature extremes. And if we're looking for an acceleration factor by using 120 degrees Celsius, then we have to make sure that when we actually once we do our modeling with our Arrhenius equation or the Norris, Landsberg, or the Coffin-Manson, once we do that equation and we assume the value of 120, that's what's in our calculation. If in the test chamber the product doesn't actually reach that temperature, then it's essentially all bets are off, right? So we violated the mathematics that went behind our test, and the results are no longer valid. So that's one of the key things, and that's why I'm showing this at this point in the slides. Is it's important to know and be sure that your product actually reaches the appropriate temperature. And that's on the high side as well as the low side. And I won't go through this in detail, but this is saying a little bit more on the kind of the same idea, as well as the CTE mismatch, and it's giving kind of a specific example. But because of time, I'm going to go ahead and skip over this one. The model shown on this page is the Coffin-Manson model. It has some similarities to the Arrhenius model, but in fact it's used specifically for temperature cycling. Okay, so this is a really good one for modeling things that have CTE mismatches across their life cycle. Or if there's a failure in a part, let's say during manufacturing, and you're concerned about whether it will last a lifetime, whether that failure for manufacturing is important, then this would be an appropriate time to use this model. Okay, so there's a couple of different variables. Again, there's the AF, which is the acceleration factor. There's N test, which is a number of cycles in the test, which is actually also N lab. So that should be in the equation. It's N lab. Down below, I have it labeled as N test for some reason, but same thing, right? So lab or test. N field is the number of cycles that it would see in the field. And what I mean by that, essentially, is the number of, let's say, usually it's the diurnal cycle, so the number of times it heats up and cools down, so it's usually once a day. And it's usually not good enough to just say once a day because it's not always the same temperature range. So this usually has to be applied for each set of temperatures like we did back up in kind of this example So we would have a certain number of, instead of a certain number of hours, it'd be a certain number of cycles at 85, a certain number of cycles at 74, so on and so forth. And then just to explain the end test or end lab a little bit better, that's the number of cycles that you're going to subject it to in an accelerated test, right? So that might be the variable that you're looking for. In fact, it usually is, given that you know your temperatures, you would probably look for the number of cycles, or you set the cycles and look for the temperature. Okay, so the delta T lab, which also could be delta T test, is the temperature change in the test chamber or in the lab. All right, so what's your total, if you're doing a sinusoidal type of temperature swing in your test environment within the chamber, what is the highest temperature and what's the lowest temperature? Right, and when I say sinusoidal, of course, you're going to go up and you're going to dwell until the product reaches the temperature, but sinusoidal in terms of you're going hot, cold, hot, cold. And the delta T in the field would be the difference between the nighttime temperature and the daytime temperature. And again, in reality, when you do this calculation for a lifetime, you're going to have a bunch of delta T's and a bunch of N's, because there's going to be delta T's for the winter, there's going to be delta T's for the summer, and depending on how much fidelity you want to apply, which would depend on your data, you'll have a bunch of them in between as well. And then there's M, which is the thermal fatigue exponent. Okay, so the M values for the low cycle thermal fatigue are different than those used in the accelerated vibration testing for high cycle fatigue, which we'll talk about here in a little bit. So for the lower that the M is, the less compression there is. Okay. So higher M's, more compression, lower M's, less compression. Typical values are between 2 and 8. Again, just like the activation energy, here's a little bit more information on the M values. There's been a variety of different authors that have experimentally determined the values of M, and we can see some of the different types of materials under the mechanism column in the middle and what their associated M value is. And this seems to be a popular thing to use for solder joints. And so I'm showing kind of the range of values for solder, which seems to be kind of 1.2 on the low side and about 2.7 on the high side. And that includes both tin-based solder, tin lead-based solder, and then lead-based or lead-free solder. So that's kind of the whole standard range of solders. And then you can see there's also a source on the bottom if you want to look at more of these. So this slide shows an example for using the Kaufman-Manson model. It's a fairly simple example. So we'll say the typical temperature swing of a component is 50 degrees Celsius. Whatever environment it is, it's probably not in an outside environment, because 50 C would be a big temperature swing. But regardless, it's 50 C for the temperature swing. And we would want to understand how many cycles are equally damaging. Okay, so the number of cycles in the lifetime of this product are 7,300. So that's what it's relative to, right? So we can assume that if we're going to test this thing with a temperature that's greater than a delta T that's greater than 50, then our cycles for our test chamber are going to be less than 7,300. Okay, we'll assume an M value of 2.5, so we don't really care what the part is, just going to assume that value. And so the first thing, you can look at these two boxes here on the left, the acceleration factors. So we saw this equation earlier where the AF equaled essentially the time or life of one over the other, and that equaled the delta T of test over normal to the power of M. So we can look at them this way, and we can directly calculate the acceleration factor. Although in reality, that's not, you don't have to do it that way. I mean, we don't need to directly understand the value of the acceleration factor. Unless there's a reason to understand it, it doesn't always provide a whole lot of value. In reality, looking at it and just doing the math in an equation like this probably makes more sense. So again, we're looking at how many cycles are equally damaging given that we have a current number of cycles, 7,300, and we know what the acceleration factor is, and we do, based on the delta t's. Well, we would have to assume one, but given that we can assume the temperature swings of the test chamber, then we can find one. And so that's what's shown here, right? So we have 7,300 cycles. Again, we have an M value of 2.5, delta T of 50 nominally out for the component typically. And then we're going to say our test chamber will do a delta T of 125. And what happens is you have roughly a factor of 10 reduction in the number of cycles, right? So it would take us 739 cycles going from low to high temperature, which would be a delta of 125 degrees Celsius, in order to be equal to the typical lifetime of 7,300 cycles at the delta T of 50. So that's essentially what it's saying. And it's important to know that the delta T of 125 here is somewhat arbitrary, right? It could be chosen to be 120 or 110, or even maybe more, 150, 200. What's important, though, to understand is that your temperature chamber, your whatever test chamber you have to test this in, could potentially be the limiting factor on that. And also, depending on what type of component you have, some components are only rated up to a certain temperature. So you have to be careful to put the temperature either too high or too low, because it could actually destroy the component outright. And then you would force other failures that you're not looking for. So that's important to understand. There has been some work to show that it's not a lot of the failure mechanisms that are being precipitated out of the components are not only dependent on the number of cycles in the delta T, but also are dependent on the how fast the temperature changes in the chamber and also in the product. Okay, so there's a little bit of work that's been done to show that, in fact, if you have very high rates of change, so for example 25 degrees Celsius per minute, which is pretty quick, that in fact the number of cycles that would be equivalent in the last example I just showed would not be 739, it would be more like 370. And that's just say that the component accumulates damage by the cycles and the delta T, but also how fast you subject it to those cycles. And essentially what that leads us to is the next model. And the next model is a Norris Landsberg model. And it includes this idea of an acceleration factor due to how fast we change the temperature. So now we have a couple of new variables, which include F lab, which is thermal cycles per 24 hours in the lab or the test chamber. And then that would be relative to F field, which is the number of cycles that something would see in 24 hours in a typical field. So it's what it's really doing, and it uses 24 hours somewhat arbitrarily, but it's essentially saying what's the ratio of the number of cycles it'll see in a test environment versus it'll see in real life, right? And it uses 24 hours because most commonly the low cycle fatigue type of failure mechanisms are the result of diurnal cycles, meaning that they're subjected to daily temperature swings, and so just naturally the Norris-Landsberg model is kind of normalized to that value. But it doesn't really matter, right? You could say that one temperature swing in the field is 4 hours, okay? Use the number of cycles in 4 hours would be 1. Okay, well, how many temperature cycles are you going to see in 4 hours in the test environment? If it's 20, then the point is that it's a 20 to 1 ratio. So you can look at it as 20 to 1, or, essentially, whatever, 40 to 2, 80 to 4. It doesn't really matter. So essentially, the Norris-Landsberg model is kind of the most extreme model, and it's important to understand that sometimes this model it may be too much to apply to a real situation, but given that you have the right information, this is probably the best and most accurate model to use because it combines the cyclic frequency, right? So the number of cycles per given amount of time, which is what we just talked about, delta temperature or the temperature swing high and low, the aging damage and the creep effects, and it's all into one thermal cycling model. So it's very nice. One caution real quick though is that, again, this is a mathematical model, and that means it's trying to match reality, but there is naturally going to be some limitations to that model. When you get to the point where the acceleration factor is really high, it is somewhat known, and it depends a little bit on the situation, but it is somewhat known that it can be risky to use a high acceleration factor. And there are some example values in here. So for example, if your acceleration factor is 50, you're probably okay. When you get bigger than 50, you start to take on a little bit of uncertainty in the model, being somewhat of a risk. And once you get to very large values, then you can just assume that it's unreasonable. So if we're going to do an acceleration factor of 1,000 or 5,000, then we're getting to the point where likely the things like the number of first of all, there's some natural limitations here, right? So you can only do so many temperature cycles and actually have your product achieve the high and low temperature. You can only do so many of those in a set amount of time. So then the reality is that you're naturally going to be a little bit limited. And if you try to force it faster, your product will not achieve those high and low temperatures. You won't have enough dwell time, and so you won't be able to actually get to it. It won't take on the amount of damage expected, and you'll have to void your results. But the point is that it's important to kind of understand that you can only go so fast. Your temperature values can only really be so big. You can't subject a part to 500 degrees Celsius and negative 200 degrees Celsius. I mean, there's some natural limitations to test chambers, to the components. You don't want to destroy the component. You're trying to precipitate a failure mechanism. So, following most of the natural limitations of the problem, in general, the results come out pretty good. I mean, you're not going to get acceleration factors in general of 1,000 degrees. So, I'm sorry, of 1,000. So it's somewhat limiting naturally, but it's just important to understand that when you go to look at your acceleration factor, you have to apply some kind of reasonable knowledge to whether it makes sense or not. Okay, so here's actual form of the Norris-Landsberg thermal fatigue model, which is kind of a build-up of a couple of different models, as we've already seen. Again, this has essentially everything in it. So each one of these terms represents the acceleration factor, which we've kind of seen on previous slides. So N field over N lab is a way to represent the acceleration factor. So it's not shown directly anywhere in the model. But we have the proportion of number of cycles in here, the dwell, the number, how fast we apply the cycles, we have that proportion in here. The extreme temperatures between the test chamber and the field, we have that in here. It's a very all-inclusive model. The last model that we're going to cover in this lecture specifically is high cycle fatigue, which is related to vibration. So we're switching from temperature as a cause of the failure to vibration. And so essentially, just like temperature, components and systems see vibration throughout their life, and it's caused from a whole assortment of different things. But you can imagine, for example, the system being manufactured, right? And then when it's finished being manufactured, it's usually tested, right? So it goes through like an ESS or a burn-in or a halt, or not a halt, but a HAS or HASA. And from there, it's usually transported to some location through a variety of different mechanisms, each of which have a different vibration profile, and then it's used in some form or fashion by the customer, which can be a whole variety of different things. Coming from the missile systems world, sometimes it'd sit in a bunker for its whole life. Sometimes it was moved around, on the asphalt, on carts and things like that. Sometimes it was taken up on an aircraft, so it had actual captive carry type of vibrations. There's also different vibrations on, of course, ground vehicles and ships and so on and so forth. So, and then actual use of a weapon had its own set of vibrations, and whatever component or system we're talking about would have its own, essentially, its own life cycle makeup of different vibrations. So one thing to kind of know right off the bat with frequencies and vibrations and the way that this kind of works, and this may ring a bell from going back to your undergrad mathematics days in some of the physics or calculus classes, but essentially in a system, there are a variety of resonant frequencies. And one of the ways that we test systems is to sweep it through a range of frequencies. And when that test sweeps through the range of frequencies, it'll often identify the natural frequencies of the system. And that's when the forcing function of the test itself, which is vibrating the unit, works in unison with the frequency of the unit, and as a result, the two work to grow uncontrollably, and that's when you have a lot of damage. And so there's no sort of damping in that situation, or usually not enough to save the system. And so identifying natural frequencies is usually a very important thing. Okay, so what this graph here shows is the inverse relationship of stress and number of cycles. And essentially what this shows is that at a low number of cycles, it'll take a high stress to precipitate a failure. At a higher number of cycles, it'll take a lower stress, right? So just as an example, look at this value of 2 GRMS, which is a vibration. This is a quantification of vibration, right? So 2 GRMS might take 10,000 cycles, whereas if the system is at 1 GRMS, it would take as much as 100,000 cycles to be equivalent. And that's shown in this equation here, right? So N1, N is the number of cycles, S is the stress. What this model here shows is very similar to what we looked at before with temperature and number of cycles. This shows, given a sinusoidal vibration input, the balance of time and stress in the field versus in a lab or test environment. So the same equivalent damage type of assessment. And you can see that there are two different forms of the equation. You can kind of look at it as, for example, 1 might be your field data and 2 might be your test environment, where you're trying to determine either T2 or G2. But another way to look at it is more kind of like the Kaufman-Manson model, where it's shown as a proportion. So the variables, T is the time at the vibration level, either in the field or in the lab. G, in this case, is a sinusoidal acceleration level, or G peak. So that's, again, it's a value for the acceleration or the vibration levels. And then B and N are the variables. Those are the ones in the exponents. So those are, B is based on the slope of the curve I showed on the previous slide. And there's some example values here where, standard values for structural metals are like 8 to 9. Solders, which are a little bit softer, are more like a value of 4. And then the N is the material damping coefficient. And the standard there is about 2.4, but it's good to know that can kind of creep up to higher values. And so there's a value of 8 as shown as being kind of on the higher end. But as a result, the typical values for sinusoidal vibration inputs tend to be around a value of 6. Now, if we go from sinusoidal inputs to random inputs, really all this stuff is the same here. The only difference really is that overall the 2b. So let me back up. Sorry, it's not exactly the same. The exponent is different. So we have b over n minus 1 here. The difference here is we have 2b over n here. So the values of b and n are the same, but kind of the overall exponents are what changes if you have random vibration versus sinusoidal vibration. So an important distinction, but again, the values are the same. And all the principles on the slide are the same. To show a quick example of the vibration, we have some data here, and I know the data is really actually kind of hard to see, and so you don't need to look at the values specifically, but essentially what this is showing is very similar to the temperature, the 10-year temperature requirement we saw several slides back. This essentially shows the vibration seen by an engine part across its lifetime, and you specifically see 2 different graphs and sets of data here. So this is just 2 examples of that same part in different geographic areas. And in fact, the full set of data has 4. But what I kind of wanted to show here was actually the importance of the different usage profiles, the life profiles of a part, and something that you might want to be aware of. And it's showing you in the context of this example. And so essentially we can take this data here and we can understand one side of the equation. Okay, so then we'll turn that into a problem by saying we want to test for a particular failure mechanism, and we want a 20-hour test. So we're really accelerating this one, right? So it's a whole life of a vehicle component. So it's a long way. We'll say 100,000 miles. So we want a 20-hour test, and we're going to look at, without looking at the data in detail, we'll just kind of take it at face value, looking at the usage of that component for different types of different uses, so different geographic locations. Okay, so same component, different geographic locations. Because of the location, the vibration data for that component changes in those different geographic locations. And what's interesting is when you work out the numbers for the same t value for the test, the g value changes quite significantly. So everything else is the same. The t value for the test is 20 hours, and we're looking for the g value of the test. The b and the n values and the exponent are all the same, but then the t and the g of the component for its lifetime changes for a through d, and that's why you're seeing the changes in this last column here. But it's interesting to point out that just by changing the geographic location in a component in a vehicle, we can see significant different vibration values, from 6.93 up to a 13.88, which is actually a very significant value in terms of vibration. So it's an important distinction. So instead of just showing you directly how to do the calculation is buried here. It's pretty simple. It's the same as the Kaufman-Manson that we looked at earlier, just with different variables. But I wanted to kind of add a layer here and show that it's important to think about your component in terms of its different environments, and geographic location may be a parameter for you, it may not. But that's an example of something you have to be aware of in terms of doing these assessments, because it can be a big factor. Okay, so one of the last things I want to discuss in this lecture is this idea of damage fractions. So we can essentially look at the total damage of temperature and vibration by adding up the different models that we've looked at. So the Arrhenius, the vibration, the Kaufman-Manson, so on and so forth. And we can look at these in a way that we can understand which one is doing the most damage, which is pretty important. So these provide the relative damage, with exposures to either temperature or vibration, so we can add up for both. one point to make here, and this is a note for the homework, is that this does not predict the life of the component. Okay, it may have that kind of flavor to it because we're talking about lifetime, number of cycles in a lifetime, but we have to be careful using these kind of to predict the lifetime, especially when we're looking at vibration mixed with temperature. It can get a little dicey. So I just want to make a note of that. It's not to predict the lifetime. Let's do one final example in this lecture, which is the exercise for damage fraction. So we'll say manufacturing performs a thermal and vibration stress screen with 10 cycles between negative 40 degrees Celsius and 85 degrees Celsius, so a delta T of 125 C, and vibration for 30 minutes per axis at 3.2 GRMS. The design life is 1,000 cycles from negative 40 to 56, and the vibration intensity is 1.2 GRMS for 10,000 hours per axis. With the criteria for a good manufacturing screen to remove no more than 5% of the design life from a product, and by the way, that's the standard number, do these intensities and durations meet the requirement? So first of all, assume a Coffin-Manson model with a B value of 2.5 for solder and a vibration exponent 2B over N of a value of 4. Okay, so this is a good point in the lecture to pause and think about this and think about what equations you're going to need, even though I've kind of told you a little bit, but think about which equations you want to use and try working this out. And with that, I'm going to go to the next slide and show you the answer. So again, this is a good time to pause. Okay, so there's, again, the thermal side and the vibration side. So for the thermal side, we use a Coffin-Manson model. The equation is the dF equals N times delta T raised up to the B. It's pretty straightforward to kind of plug the numbers in and see what the value is. It's shown, the thermal screen is shown right up here, 1.75 times 10 to the negative 6. Okay. The design life is this value of 9.03 times 10 to the negative 6. And so you can think about design life, percent life taken out. So not the design life is how long it's intended for. So you can think about how much your thermal screen takes out of that design life as a percentage, right? So this is a way to think about the damage, right? So we can just divide the two, and that'll give us an idea. Keep in mind that the design life is to the power of 7 and not 6. So there's quite a big difference, and that's why when you divide the two, you get that the thermal side is taking out 1.9% of the life. Okay, and then similar kind of process for the vibration. In this case, the damage here is 52.4. The design life is a value of 20,736, and as a result, the percent of design life taken is 0.25. So overall, if you add the 1.9 and the 0.25, you get much less than 5, and as a result, we would say that the requirement is met. So to summarize today's lecture, first of all, we've covered the primary goal of today's lecture was to look at damage equivalence using a variety of different models. And so one of the important things here is that the value of using these depends on the way you look at your problem. It may be that you know the life, and so as a result of knowing the life of the system, you want to find some equivalent types of tests that you would apply in a test chamber to look at the life and say, is anything going to occur in the life? Or maybe instead of looking at one life, a lot of times what we do in reliability engineering is look at 3 lives. So you may look at, there may be 1,000 cycles at a delta T of 50 in reality, and you want to find out, okay, that's 1 life, what is 3 lives, and then what would be a test I could design for 3 lives to make sure that my system doesn't have any of these failure mechanisms in it. But then there's other opportunities too where you may find a failure mechanism either in the field or in manufacturing and you also want to understand what's the risk to other units seeing this. And so you can design a test, again, kind of based on lifetime to understand whether that's going to occur or not. So that's kind of the primary goal, was to bring up and show you these different models and how they can be used to accelerate what you would see in reality, and this idea of accumulating damage, and that it's important to understand that you can accumulate damage from in different ways. You can accumulate some damage from vibration, some from temperature, and so those can be looked at together. And then to end it, there are a variety of different references here which you can go check out. All right, thanks everybody.